Hello everybody. In this video we're going to be going over section 11.4, Colligative Properties. This is going to be a longer section and the majority of our questions this week are going to come from this section. So the first thing we're going to learn is how to express concentrations of solute components using mole fraction and molality. We'll describe the effect of solute concentration on various solution properties including vapor pressure, boiling point, freezing point, and osmotic pressure. We'll perform calculations using mathematical equations that describe these various colligative effects. We'll describe the process of distillation and its practical applications. And finally, we'll explain the process of osmosis and describe how it's applied industrially and in nature. First, let's do a little review of our concentration units. So when we're talking about molar concentrations, we have three different concentration units that we're particularly interested in. So far, we've seen quite a bit molarity, all right? And this is going to be the moles of solute divided by 1 liter of solution. This week, we're going to need to focus in a little bit more on one that we have seen, but not quite as much, molality. And this is going to be the moles of solute, just like it was in molarity, but instead this time we're going to divide it by 1 kilogram of solvent. So the key here is that here we're talking about the solution, which includes the solvent and the solute, and here we're talking just about the solvent. Also here we have volume, and here we have mass. Then finally, we'll talk about mole fraction, which is going to be the moles of one of the components divided by the sum of all of the moles that are in that solution. So that's our mole fraction. Literally, what fraction of all the moles are of type A. So let's talk a bit about converting from molarity to molality. I know that there's a lot of math here, but I want to step through this with you. Don't get overwhelmed. And I need you guys to realize that while this is a little confusing, part of the reason that it's confusing is because we've gone out of our way to make it a little bit easier for ourselves. So let me show you what I mean by that. When we have molarity, this is going to be the moles of the solute divided by the volume of solution, where the volume of solution is equal to 1 liter. And what makes this a little bit easier for us is that if we just assume that we have 1 liter of solution, the molarity is going to be numerically equal to the moles of solute. All right, so we kind of get that for free because this value here is just 1. All right. So if we know the molarity and we have 1 liter of solution, we know what the moles of solute is. So what we're going to do is we're going to assume that we have 1 liter. And we're going to put that down here for our volume of solution, 1 liter, and we're going to multiply that by the density. Don't forget that you need to adjust these units here. You may not have been given the density of the solution in units per liter. So you may need to make a conversion there in order to get these units to work out. Then that's going to give you the mass of the solution. And as we talked about earlier, the mass of the solution is the mass of the solute plus the mass of the solvent. But when we're doing molality, we need to know the mass of just the solvent. So we need to take the mass of the solute out from this. We need to remove it from the mass of the solution. So we're going to have the mass of solution minus the mass of the solute. How do we know how much the solute weighed? Well, that's going to be the moles of solute that we knew from before multiplied by its molecular weight, which we're going to need to calculate from the periodic table. After we've removed the mass of the solute, we're going to have the mass of just the solvent. And then we can plug that into this equation down here. But remember that it has to be in units of kilograms. So we may need to make a conversion between this final mass of solvent that we got before we put it into that equation. The moles of solute, again, we knew from the very beginning because we did that clever thing where we made the volume 1 liter. let's talk about converting from molality back to molarity. So when we had molality, and notice that when we do molality, we make it like an italic here, which is easy for me when I'm typesetting. But the reason we do this is to make this distinct from mass, because they're both lowercase m's. So when you see an italic lowercase m, I'm talking about molality. And you may want to do something clever when you're writing it down in order to keep that clear for yourself, because I know it's a little hard to write things in italic. But that's going to be the moles of solute divided by the mass of solvent, where the mass of solvent is again equal to 1 kilogram. So just like before, if we know the moles of solute, or if we know the molality, we're going to know the moles of solute if we just assume that we have 1 kilogram of solvent. So what we need to do is we need to figure out the mass of the solution. So we're going to take this 1 kilogram of solvent, we're going to plug it in down here. Again, we're probably going to want to convert that to grams when we do this. And then we're going to need to add the mass of the solute. How do we know the mass of the solute? Same way that we did before. We're going to take the moles of solute from up here, and we're going to multiply it by its molecular weight. Finally, we need to get the volume. So now we have the mass of solution. Finally, we need to get the volume of the solution. So what we're going to need to do is plug this mass in down here and divide it by the density of the solution. Again, remember, you need to match these units up so that they cancel. And then before you take that volume of solution and plug it in to get our molarity, we need this volume to be in liters. All right. Now let's talk about how to get to molality to mole fraction. All right. So a lot of times when we're talking about mole fraction, we're talking about a situation where we have multiple solutes. Okay. It's not always true. It could still be just a binary mixture of one solute and solvent, but you may come into a situation where you have multiple solutes. So if that's true, we need to know the concentration of each one of those. So I could have the molality of one component, the molality of B component, the molality of C component. And I'm going to know the moles of A right off the bat. I'm going to know the moles of B right off the bat. I'm going to know the moles of C right off the bat. So that's pretty nice. We've gotten most of the numbers that we need right off the bat just by inspecting this and assuming that we have that 1 kilogram of solvent that we have here. All we need to know is the moles of solvent. Okay, so we're going to take that 1 kilogram value. We're going to convert that to grams typically, and we're going to multiply that by the molecular weight of the solvent. We'll know the moles of the solvent now. After that, we just need to figure out our fractions. So the mole fraction, and this is a capital Greek letter chi, just in case you're wondering, but you can use X, whatever, of A is going to be the moles of A divided by the sum of all the other moles. All right, I didn't subscript that. I need to subscript that. But moles of A plus moles of B plus moles of C plus the moles of the solvent. All right. If I wanted to know the mole fraction of B, I would just replace the moles of A with the moles of B. Okay, now that we've reviewed our units, let's talk a little bit about colligative properties, and we'll see how those units are going to come into some of the equations. So, we know now that solution properties differ from those of the pure solutes and the pure solvents, right? The densities may be different. Other values may be different between them. But most of the time, this deviation in the properties is going to depend upon the identity of the solutes and the solvents. However, there are a few properties, the colligative properties, that depend only on the concentration of the solute. So it doesn't matter what solute you have, all right, it's going to affect these colligative properties the exact same way. And these include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. All right. We're going to see that as we add solute to a solvent, it's going to lower its vapor pressure, it's going to increase the boiling point, it's going to decrease the freezing point, and it's going to affect the osmotic pressure. So let's talk about what these are. First, vapor pressure. Vapor pressure is the partial pressure of a liquid at equilibrium. All right. So if I have a liquid, some of it's going up into the gas phase. When the pressure of that gas above it, when the partial pressure of that gas above this liquid is equal to the vapor pressure, then equilibrium will be reached, and just as much gas will be going into the liquid phase as liquid will be going into the gas phase. The liquid will, in effect, the net change will stop, and we won't see any decrease in the volume of the liquid anymore, and we won't see any increase of the concentration of the gas once we've reached our vapor pressure. When a solute is dissolved in a liquid, the vapor pressure will be lowered. The reason for this is because the solute molecules are occupying sites at the liquid surface, blocking the solvent molecules' access to the gas phase. So you could just imagine that these solutes are on the top of a liquid, and they're not letting the solvent molecules escape anymore. What can still happen, though, is that solvent molecules can recombine with the liquid phase on top of the solute molecule. So it's not preventing the gas molecules from coming back in, all right? It's only preventing the liquid molecules from escaping. So the overall net result is fewer solvent molecules in the gas phase. There is a mathematical relationship here. It's called Raoult's law. The partial pressure exerted by any component of an ideal solution, remember ideal solutions are ones that are driven entirely by entropy, is equal to the vapor pressure of the pure component multiplied by its mole fraction in the solution. All right, so we know the vapor pressure of pure solvents. This is a thing that we can just go and look up, all right? And if we multiply that by the mole fraction, which is again just the fraction of the overall solution that is that solvent, that will be the partial pressure, the vapor pressure of that component on the solution, exerted by the solution. We can combine Raoult's law with Dalton's law, which said that the sum of the partial pressures is the overall pressure, okay? And we can replace the partial pressure of the components with their mole fraction multiplied by their pure partial pressure, okay? Now I know that there's a lot of different symbols and stuff here, so we need to keep it straight. When I have an asterisk, I'm talking about the partial pressure, the vapor pressure of a pure solvent. And when I don't have an asterisk, I'm talking about the partial pressure that we see in a solution. All right. Now, when we restrict ourselves to just non-volatile solutes, right? So here we were assuming that we were going to have different components that were all able to move out into the gas phase. But if we talk just about non-volatile solutes, where their partial pressures of their pure states are essentially zero, okay, we get a simplified equation here, where the pressure, the vapor pressure of the solution, its partial pressure, is just going to equal the mole fraction that is due to the solvent multiplied by the pure solvent's partial pressure. All right, so in a lot of ways this is pretty intuitive. All right, if I just had the solvent all by itself, it would have this partial pressure. I put it into a solution. What I need to do now is figure out how much of that solution, as like some decimal value, is still the solvent, and that will give me the partial pressure of the solution. Raoult's law can be used to prove that the vapor released by a solution will be enriched in the less volatile components. So I've spared you some of the math that happens here. It gets just a bit confusing. But what's basically going to happen is that less volatile components are going to get enriched down here in the liquid phase. So the less volatile components are going to want to stay in the liquid phase, and the more volatile components are going to move up into the gas phase. All right. So this gas phase is going to be enriched, meaning its mole fraction is going to be higher for the non-volatile component, and then when we recondense it, we get more of that non-volatile component that actually managed to make it through the distillation setup and over to the receiving flask. So down here, we're enriching non-volatile components. Over here, we have more of the volatile components. So boiling point elevation is the result of the vapor pressure lowering. Okay, as we saw over here, the overall vapor pressure is only going to be some fraction of what it used to be. And as we talked about before, boiling occurs when the partial pressure of that solution is equal to the atmospheric pressure. So if adding a solute is going to lower our partial pressure, it's also going to increase the temperature required in order to get the vapor pressure to equal the atmospheric pressure. All right, I'm going to have to add more heat. I'm going to heat it up and get it hotter in order for that vapor pressure to equal the atmospheric pressure. We can figure out how much temperature is going to be required in order for this to happen. We have an equation for that. All right, and it is delta T boiling. All right, so the change in boiling temperature is going to equal Kb, which this constant is specific to the solvent, times the molality of that solvent. Now remember that this is a change in boiling temperature, okay? Meaning it's going to be the final boiling temperature after we've added the solute minus the initial boiling temperature of the pure solvent. Kb is called the boiling point elevation constant. Okay, let's talk about freezing point depression. We have seen this in our lives before. When we have icy roads, we add salt to them, all of a sudden that ice will start to melt. That is an example of freezing point depression. Okay, we've lowered the temperature required to get something to freeze. All right. So just like when we added the salt to the water, the solution freeze at lower temperature than their pure liquids. Freezing point depression is directly proportional to the molality of the solution. So again, the change in temperature that we get for that freezing point is going to equal something called the freezing point depression constant, this Kf. You may also see it called the cryoscopic constant, times the molality of that solute. Here are some Kb and some Kf values for various different solvents. Again, it does not matter the identity of our solutes for the colligative property. It only matters the identity of our solvents. All right. So typically, these are going to be our boiling points and freezing points. We need to know what these points would be if we want to figure out what the new temperatures are going to be when we add our solutes. Because remember, these equations are only giving us the change in temperature here. I still need to do some math to figure out what the new freezing point would be if I'm given the change in temperature, which means that I need to know what the old boiling point or the old freezing point would have been, and I need to know the Kb and Kf values. The effects of colligative properties are seen pretty readily in a phase diagram. This is pretty useful to us. Where our solid lines here would be for the pure solvent, and our dashed lines now represent the new properties, the new phase boundaries that we're going to see once we add our solute. Okay, so this difference here is going to be our change in boiling temperature. This difference here is going to be our change in freezing temperature. Okay, you can see that we're moving these values out. All right, increasing the amount of temperature and pressure, the area of temperature, the different temperature pressure values that would maintain a liquid in this case. Okay, so we're decreasing the amount of temperatures and pressures that produce gases and decreasing the amount of temperatures and pressures that produce solids. You can see that colligative properties do not affect the boundaries between gases and solids. All right, they only affect the boundaries between gases and liquids and solids and liquids. Osmosis. So, some membranes only allow molecules or ions of certain size, shape, polarity, etc. to pass through them. The use of membranes in chemistry and industry is very, very important, and we've been able to tailor them such that they're only going to allow certain chemical species to go through them. These types of membranes are called semi-permeable. Osmosis occurs when we set up three specific conditions. All right, we have a semi-permeable membrane. It's separating two solutions, or a solution and a pure solvent. Okay, the same solvent exists on either side. Only the solvent molecules can permeate the membrane. The solute molecules cannot permeate the membrane. All right, so we only can have the transition of solvent across this membrane. And what's going to happen is solvent molecules will diffuse across the membrane in both directions, but at different rates. This is called osmosis. Again, there is an equation for this. The net effect of osmosis is solvent molecules accumulating on the side of the membrane with a more concentrated solution until one of two conditions is met. The concentration of the two solutions is equal. The pressure differential across the membrane is equal to the osmotic pressure. Okay? And the osmotic pressure is this capital Greek letter pi, and it's going to equal the molarity. So before we were dealing with molality and mole fraction, but now we're dealing again with molarity, times R, which is the gas constant, times T, which is the temperature. All right, so let's see what we're talking about here. Here we have an example where we have a solution on one side with some solvent molecules, and we have pure solvent on the other side. The solvent molecules are allowed to pass across a semi-permeable membrane. Now what's going to happen is the pure solvent molecules are going to move over to our solution. And in this case, that process would be pretty much indefinite because we're never going to have the same concentration on either side. All right. But eventually we get a pressure differential, right? There is energy, pressure being required to push this liquid level above this liquid level. They're going to want to find their level initially, but eventually there will be a pressure differential. At that point, this process will stop, okay, and we will be at an equilibrium in this situation. Now, you guys may have heard of reverse osmosis. This is used pretty widely in industry to purify liquids, specifically water. A lot of times you'll see them inside of your house and stuff like that. And what is happening here is that we have this semi-permeable membrane and we push down on the one side, applying pressure, and force solute molecules, often water, through that semi-permeable membrane to the other side. Okay? Now, this tends to look a bit like filtration, right? But it is a little bit different. And the big difference being that when we still allow for there to be some solute molecules on this side, this pressure is going to be less than what would be necessary to purely filter a solution. Okay? Also, the solute molecules in an industrial process aren't going to build up on this membrane, but instead be swept away. Okay? Large scale osmosis, all right, what it basically winds up doing is it makes a whole bunch of water, just a little bit more concentrated in solutes and all those impurities that we want to remove, and takes a small amount of water and makes that very, very pure, removing all of those solutes. Okay, let's talk about isotonic versus hypotonic versus hypertonic. So this is again a special situation, and it's well modeled by looking at blood cells. So here we have a semi-permeable membrane, but it's completely surrounding an internal solution. Okay? So in this case, the outside solution could be having the same concentration of solutes, in which case their osmotic pressures are going to be equal, and they would be isotonic. And that's the situation under normal circumstances inside of your blood. Okay? The plasma portion of your blood is isotonic with the inside of the red blood cells. When a solution is less concentrated than another, it's called hypotonic. So what's going to happen if I inject your plasma with a solution that is less concentrated? I will have increased the number of solute molecules on the outside of the blood cell. They're going to go and want to, the osmosis is going to carry them inside of the blood cell. They're going to start filling this sac up with extra solvent molecules. And eventually that pressure could actually cause them to rupture. Okay. On the other hand, when a solution is more concentrated than another, it's called hypertonic. So if I injected plasma into you that was hypertonic, what's going to happen is I'm going to decrease the overall free solute molecules on the outside of this cell here, and it's going to draw those solute molecules, those water molecules, out of the cell. All right, and your cells are going to shrivel up, and then they're going to die. All right, this is also a bad condition. The moral of this story is that this is why we have saline solution instead of pure water that you're given typically when you need fluids in the hospital and stuff. And the concentration of that saline solution is very, very important. Okay, that saline solution needs to be isotonic with your existing blood plasma. All right, so we're going to have some problems where we're going to determine the molar mass using our colligative properties. All right, so it's a nice little feature that almost all of the colligative properties can be used to determine molar mass. And the process for this is going to be pretty much the same, independent of what we're doing, just a little bit of different equations and math. What we're going to do if we want to use a colligative property to determine the molar mass is we're going to add a known mass of solute to a known amount of solvent. Okay, so I start by weighing out some solute, and I can weigh out or measure out the volume of a solvent. All right, I'm going to measure the colligative property. So I'm going to take a pure solvent and I'm going to measure its freezing point, for instance, or I'm going to measure its boiling point, or I'm going to measure its osmotic pressure. And then I'm going to take this new solution that I've made, and then I'm going to measure its freezing point or its boiling point or its osmotic pressure. All right. And I'm going to be able to tell the difference in those freezing points or boiling points or the osmotic pressure difference. Okay. After that, we're going to calculate the concentration, whether that be molality or molarity of the solute. So I'm going to invert my equations here. I'm going to get molarity or molality or molarity. All right. We're going to determine the number of moles present. So because I put in a known amount of solvent, I can figure out the moles of the solute that I added from these concentrations. All right. And then because I massed out the solute, I know the mass of that solute. I'll divide that by its moles, and I'm able to get its molecular weight. And we can see that molecular weight can be very important, so it's nice to have this method of calculating that. Our final thing that we're going to cover is when we have electrolytes and colligative properties. So basically what happens is, just like when we saw with electrolytes before, we're going to see dissociation. All right. So if I put one sodium chloride molecule into water, it's going to dissociate into two different ions. Both of those ions are going to exert these same colligative properties. All right. The chloride ion is going to be able to take up a spot on the top of a liquid and lower its vapor pressure, and so is the sodium ion. All right. So to account for this, when we have electrolytes, we add something called the Van't Hoff factor. All right. And roughly the Van't Hoff factor would be the moles of particles in solution divided by the moles of formula units dissolved. So in the case of sodium chloride, where we have sodium ions and chloride ions being released for every one sodium chloride formula unit we add, okay, the top here is going to be 2 for our 2 different ions. The bottom here is going to be 1. Our I factor will be 2. All right, and we just add that little fudge factor into our equations, and we can still use these equations to calculate our colligative properties.